common complaint about R is that it's quite slow in comparison to compiled languages such as C or C++. In this chapter, we'll look at a few ways to speed up R. In order to investigate how fast certain chunks of code run, we need a mechanism to do the timing. There's a package called microbenchmark that allows us to repeatedly run code and times it. By default, it runs each code block 100 times and then reports the 5-number summary of the run times. Remember, the 5-number summary is the minimum, the 25th percentile, median, mean, 75th percentile, and then maximum amount of time that it ran. The column CLD stands for compact letter display, and it tests whether or not there is a statistically significant difference between the two methods of running the code. So in this little example, we see that the square root function is drastically faster than the more generalized power function for calculating the square root. Our example problem for now will take a data frame with 4 numerical columns, and for each row, I want to calculate which column of the 4 had the largest value. At the heart of this is going to be the function which.max, which takes a vector and returns the index of the largest value. Our first example function creates an output vector, and then using a for loop to go through each row, it'll use the which.max function to determine which column was the largest. Once we are done with the for loop, we'll return the result to the calling environment using a return statement. If you look through example R functions online, you'll rarely see people using the return statement, and instead they'll have the final line of code in the function contain the output object. I think that the return statement is much easier to read, but online people insist that the return statement is so much slower. Let's find out if that's true. It turns out there isn't a practical difference in runtime, so I prefer to use the more readable return statement. Another question I've wondered about is if it makes sense to allocate in memory the whole output vector prior to running the for loop, or if I should just add on to the output vector at each step. Again, the answer turns out that it doesn't matter, and we could just use the simple initialization and not worry about the length. It turns out that for loops in R are actually really slow. To demonstrate this, we'll use the apply function, which applies a function to either the rows or the columns of a matrix or data frame. Using an apply function turns out to be about 10 times or more faster than writing a for loop, and as a result, people recommend never writing for loops in R if you can avoid it. dplyr functions are generally more readable, but is there a performance hit in using the dplyr package compared to the apply functions? For small data sets, it turns out that there is a small hit, and dplyr is slightly slower, but it is very small. It's in the microseconds. When we look at a larger data set, it turns out that dplyr is actually faster because there are some optimizations for dealing with column summarizations and column-wise actions. For small data sets, it doesn't really matter because R is already fast enough. But when we have large data sets and it matters, dplyr is actually faster than using the apply functions. In order to take advantage of multiple processors on your machine, it is necessary to intelligently divide the work up across those processors. Because there is some computational cost in copying the data and instructions to each processor and then gathering up the results, there's some inefficiency introduced, and we shouldn't expect that a program to run twice as fast just because it has access to twice as many processors. So to minimize how often this copying and gathering inefficiency is introduced, we want to divide the work into as large a processing chunks as possible and then gather them up. Many of the resampling methods common in modern statistics are embarrassingly easy to parallelize. Bootstrapping, for example, creates thousands of bootstrap datasets by resampling the original data and then running the analysis routine on the bootstrap data. If I have 6 processors, then I'll take my thousands of data sets and divide them into 6 groups and pass those groups to each of those processors. Then for each bootstrap data set, I'll calculate my model results, and then once all the processing is done, I'll gather up the results from all 6 cores back into my original program. The boot function requires the user to write their own function that takes in the original data plus an index of what things should be resampled. In this case, we're going to create a linear model using the bootstrap data using this index thing, and then we are going to just return the model coefficients. The boot function has a couple of options that allow you to utilize as many CPUs as you want. You just need to specify the backend to do the parallel processing and then the number of CPUs to use. Likewise, the machine learning package caret allows the user to specify to use multiprocessors as well. The for each package has a replacement for the for loop that does the parallel processing automatically. All we have to do is use the for each function instead of the for, and add this extra %do_par%, which actually specifies to for each to actually do the parallel processing. While using the tidyverse set of functions, R is generally fast enough and often performs similarly to Python. Unfortunately, though, speeding execution up even more requires writing code in a compiled language such as C or C++, and then writing a wrapper package to call that resulting executable. Unless your package is being used by hundreds of people, it generally isn't worth spending 10 hours of pain and effort to write dedicated C and C++ code just to save a minute of execution time. This has been Derek Sondrager, and thanks for watching, and as always, thanks to the R community and R Studio for such a wonderful set of tools.